we have been solving problems related to entropy transport across a control volume. We will work out a few more problems in this lecture. So, the next problem is problem number 7.10. A frictionless piston cylinder is loaded with a linear spring with a spring constant of 100 kilonewton per meter and the piston cross sectional area is 0.1 meter square. The cylinder initial volume is 20 liter, it contains air at 200 kilopascal and ambient temperature 10 degree centigrade. The cylinder has a set of stops that prevents its volume from exceeding 50 liter. A valve connects to a line flowing air at 800 kilopascal 50 degree centigrade as shown in the figure. The valve is opened allowing air to flow until the cylinder pressure reaches 800 kilopascal, at which point the temperature inside the cylinder is 80 degree centigrade. The valve is then closed and the process ends. Is the piston at the stops at the final state? Taking the inside of the cylinder as a control volume, calculate the heat transfer and net entropy change during the process. So, let me draw a schematic of this problem. This is the air supply line. There are some stops So, what is happening is air is flowing in this line and it is supplied so that this piston expands and it might hit the stop or not. From the data we have to figure out whether it hits the stops or not. So, when the piston is moving, how the pressure is related to the change in volume. So, you have the force for a linear spring, force is proportional to the displacement. So, F is equal to K into delta x, right. Delta x is delta V by A, where A is the cross sectional area of the piston and F is delta P into A, right. So, the net force some delta P into A, right, some P minus P reference. So, this is just to let you know that the pressure versus volume curve will be a straight line with a slope of K by A square. So, you can write say P stop minus P 1 is equal to K by A square into V stop minus V 1, right. So, K is given, the spring constant, this is 100 kilonewton per meter. Cross sectional area is 0.1 meter square, okay. V stop minus V 1, so initial volume is given 20 liter, you convert this to meter cube, initial pressure is 200 kilopascal. So, P 1 is 200 kilopascal, so from here you get what is P stop, area of cross section is given, what is that, 0.1 meter square. So, you will get what is P stop. P stop is 500 kilopascal. Now, from this data, what is this P stop? That means the pressure when this just reaches the stops. From these data, can you tell whether it hits the stops or not? See, the final pressure is told as 800 kilopascal, which is more than this. That means until and unless it hits the stops, pressure cannot be more than this pressure when it comes just before the stops. So, because P2 is greater than P stop, P2 is 800 kilopascal. So, that means it hits the stops. See why thermodynamics problems are so interesting. I may plan for setting up exactly this same problem in your exam, but I change the final pressure from 800 kilopascal to 400 kilopascal. Then entire solution changes, because then the piston no more hits the stops, it comes before the stops and the solution is different, although conceptually it is a similar problem. So, this makes thermodynamics problems very interesting, because the solution of the problem, how it is evolving, it depends on the data which comes as a part of the intermediate calculation. That does not make problems very stereotype, where you have a unique approach of solving the entire problem. So, then what is required is basically the entropy generation. So, let us write what are the states. The inlet state is 800 kilopascal, 50 degree centigrade. State 1, (200 kilopascal), 20 liter, 10 degree centigrade. State 2, 800 kilopascal, 80 degree centigrade. Okay. And T0 is this one, 10 degree, 273.15 plus 10 Kelvin. Ambient is 10 degree, that centigrade, that is given. There is no exit, right, only it is a tank filling with a variable area, that is the problem. So, if we apply the first law for the control volume, which is the cylinder, it is a uniform state uniform flow process. So, Q plus Mi Hi is equal to M2 U2 minus M1 U1 plus Me He plus W. So, there is no exit, therefore, this is 0. What is W? Here there is a W. As I told you earlier, and you should remember this very carefully, the work done equal to integral PdV does not depend on whether it is a control mass or a control volume. So long as you have a moving system boundary in a quasi equilibrium process, you can write PdV. So, this is integral of PdV from 1 to 2. So, half of P1 plus P2 into V2 minus V1. So, this is actually not P2, this is P stop into V stop minus V1, because after reaching the stop there is no work done. After this piston reaches the stop, there is a constant volume process, so there is no work done. So, this is the final pressure, so far as this formula goes, is the pressure when it just reaches the stops. So, if you consider the PV diagram for the process. So, 1 to 2, 1 to stop it is like this, and from stop to 2 it is like this. So, this part has no work, so only this part has work. Then this tank, is it this cylinder, is it insulated? It is not insulated. So, you have to basically find out what is the heat transfer. State 2 is known, so this is air, right. You can see, look at the temperature range, it is not that much, 50 degree, 10 degree, 80 degree, this range of temperature you can assume constant CPCV. So, Mi is M2 minus M1. So, how do you know what is M2 and M1? So, you can use the ideal gas law, right. So, P1 V V1 is equal to M1 R T1, right, and P2 V2 P2 V stop or P stop V stop P2 V2, V2 is same as V stop, is equal to M2 R T2. Okay. So, from these two you can calculate what is M2 and M1. So, I do not have the data for M2 and M1, but you can calculate this, and Mi is M2 minus M1. So, once you calculate these values and you can, so Mi, when you write M2 minus M1, then you can split this into two terms, one is with M2 and another is with M1. Then H you can write CPT and U as CVT. Okay. So, with constant CPCV you can replace all these as functions of temperature, and then you will get what is Q. So, that answer I have, Q is equal to, so in this equation if you substitute everything, so Q is minus 11.6 kilojoule. Okay. So, why do you require Q? Because for entropy generation you require Q. So, if you apply the second law, so change in entropy M2S2 minus M1S1 plus MESE minus MISI is equal to Q by T, T0 plus entropy generation. There is no exit, other values Mi is M2 minus M1, and you can use the change in entropy formula for ideal gas. So, if you do all this you will get entropy generation as 0.063 kilojoule per Kelvin. Okay. So, we will work out a couple of more problems. Let me erase this one. Problem number 7.11. 11. A certain industrial process requires a supply of 0.5 kg per second of air at 200 meter per second at the condition of 150 kilopascal 300 Kelvin. This air is to be exhaust from a specially designed turbine whose inlet pressure is 400 kilopascal. Okay. The turbine process may be assumed to be reversible and polytropic with polytropic exponent as 1.2. What is the turbine inlet temperature? What are the power output and heat transfer rate for the turbine? Calculate the net rate of entropy increase. This is essentially entropy generation. If the heat transfer comes from a source at temperature 100 degrees centigrade than the turbine inlet temperature. So, this is a turbine which produces some power output and it also produces steam at a given pressure, temperature, mass flow rate, etc., that is used for some chemical processing.
So there is a velocity.
There is a velocity also, right. So, we call this as I and we call this as E, that is better, because for the turbine, that is the steady state steady flow picture, we have one inlet and in this case one exit. So, I and E are our usual symbols. Okay. So, what is told that there is a heat transfer to the turbine. This takes place from a heat source at temperature TH. Okay. So, let us note down what data is given. Pi is 400 kilopascal, PE is 150 kilopascal, TE is 300 Kelvin, m dot is 0.5 kg per second and VE is 200 meter per second. The turbine process is reversible and polytropic with n is equal to 1.2. So, that means the process in the turbine can be described by pressure into specific volume to the power n equal to constant. If this n is Cp by Cv, then it is reversible adiabatic. For air, that Cp by Cv, if you take constant Cp Cv, it is 1.4. Here the value of n given is 1.2, that means it is not reversible and adiabatic. It is reversible but not adiabatic. This is the first message that we get from here. But if this is followed and also Pv by T is equal to constant, so from here for reversible polytropic process, this much we can write. So, all these things are known except Ti. So, Ti is 353.3 Kelvin. Okay. Now you need to find out what is the heat transfer, because entropy generation depends on that. So you apply the first law for the turbine as control volume. Okay. So Q dot plus m dot I. Now here kinetic energy term is there, so let us write the full thing and see what we neglect. Okay. So Vi nothing is given, but we can neglect this one. You can neglect the difference between these two. You can neglect sorry, you cannot neglect anything else, this is given. So this you have to use the data. Hi minus He you can write m dot I and m dot E are both m dot, Cp into Ti minus Te. What is this one? So remember, this is a reversible steady state steady flow process with single inlet and single exit. So you can use the VdP formula, right. So this will be minus integral of m dot into VdP from I to E. This is very important, not PdV. Okay. So we showed that the limiting case of reversible isothermal process satisfies this formula, the limiting case for reversible adiabatic process satisfies this formula, and any reversible process can be thought of as a succession of a large number of reversible adiabatic and reversible isothermal processes. Therefore, for this polytropic which is not adiabatic but reversible, you can use this formula. So now you can straight away V, you can express V in terms of P, that is C to the power 1 by n by P to the power 1 by n, right. So then that integration becomes minus m dot, let us write this term, C to the power 1 by n, then P to the power minus 1 by n dP. So P to the power minus 1 by n plus 1 by minus 1 by n plus 1 from I to E. So this VdP integration, this is minus actually. So P to the power minus 1 by n into C to the power 1 by n is V, right. So minus m dot Pe Ve minus Pi Vi into n by 1 minus n, sorry, n minus 1, right. So this is the work done. You can substitute all the values. The specific volume you can calculate by using PV is equal to RT, okay. Then because this is air which you can approximate as ideal gas, so from here you can calculate what is the rate of heat transfer. So very interesting problem where you do not have reversible adiabatic, any reversible process with heat transfer in the turbine. So this is 19.2 kilowatt, okay, and Then we can apply the second law for the turbine. So, m dot into SE minus SI is equal to Q dot H by TH plus rate of entropy generation, right. So, SE minus SI, again you can use the ideal gas formula, Q dot H you have calculated, so you will get what is entropy generation. So, entropy generation is 0.0163 kilowatt per Kelvin. So, you can attribute this entropy generation due to two things. One is heat transfer, and the heat transfer, the associated external irreversibility associated with heat transfer, because within the turbine the process is reversible. So, that will not give rise to any entropy generation. Okay. So, let us work out another small problem. We have a little bit of time in this lecture, so let us utilize that. Problem 7.12, this is a sort of review problem. A small pump takes in water at 20 degree centigrade 100 kilopascal and pumps it to 2.5 megapascal at a flow rate of 100 kg per minute. Find the pump input, power input. So, the key to this problem is that it is a small pump. So, heat transfer is negligible, and if you assume the pump to be reversible, because no other data is given. So, the work done for the pump is given by the integral VdP formula. So, the work done minus integral VdP from pump inlet to pump exit. So, the pump takes in water at 20 degree centigrade 100 kilopascal and it pumps to 2.5 megapascal. The specific volume, see this is what, as pump as an engineering device you must have an idea. Pump handles a fluid which is virtually incompressible. So, that means this V is roughly constant. So, because this V is roughly constant, you can take this V out of the integration. So, this approximately, not exactly constant, but approximately constant. So, this is minus V, integral of dP is P minus Pi. P is 2.5 MPa, Pi is 100 kilopascal, and this V is specific volume roughly Vf at 20 degree centigrade, which 1 by Vf will be roughly like 1000 kg per meter cube, the density of water. So, you have to find out what is the rate of work done. So, W dot is m dot into small w, and m dot is given as 100 kg per minute. So, you convert it into kg per second. So, this will be roughly minus 4 kilowatt, that is the work input necessary for the pump. We have solved quite a few problems in the control volume analysis for entropy transport. We will continue with discussions on similar lines in the next lecture. Thank you very much.